Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we have started discussing the risk assessment and the reliability of spacecraft system. So, in the last class we discussed that is how we do the ground simulation of the space environment and do the test and evaluation for space qualifications, and we defined what is called the reliability and the defined the reliability and the failure function. So, in this session we will continue with the reliability and failure function. Then we will discuss the failure probability density function and then failure or the hazard rate. So, we already the first two topics we introduced, but we will still continue with the failure or the hazard rate. So, I will just start with the again will whatever we discussed we will write down again. This is the reliability . So, it is already we said it is the probability that a product or a system or it can be service like the communications service or navigation service, it will operate for the intended functions or services over the specified time duration under the given environmental condition. So, this is already we have seen, we will go ahead. So, now let us consider at t is equal to 0, there are n 0 components. There are n 0 components. There are n 0 components, and at time t, let us define n s is the number of components those have been successfully tested. Tested. So, this means the test result is success, and NF here the failed component. So, this is the successful components failed components. So, now I can write whatever the probability definition, this is the classical definition of the probability, R t is equal to n s t by n 0. So, here t is a continuous random variable. So, now suppose if I consider at t is equal to 0, t is equal to 0. So, R 0 will be equal to 1, because at t is equal to 0 n s t is equal to n zeros, and when t is equal to infinity. So, R of infinity, it has to be equal to 0. Why? Because no components can perform for infinite period. So, I can write that is the probability for failure, probability of failure, that is equal to f t is equal to 1 minus R t. So, this is what is R t we have defined. R t means P capital T greater than T. What is capital T? Capital T is the time at which the component fails. So, now I can write this, since this is a cumulative probability function. So, I can write 1 minus p t like again p t So, what does it mean? That now it is the t, since it is the time at which it is failing. So, if the time is more than that t, means it is a failure function. So, I can write it like that. So, if you see this curve shows a particular the cumulative probability function for the reliability R t. So, what does it mean? That again whatever we say is when t is equal to 0, the reliability R t is equal to 1, and whenever, so at t is equal to 0, it is having it is no failure. So, R t is equal to 1, and whenever now the time is increasing. So, the reliability is decreasing. So, the reliability decreases, as the life of the component or product increases. So, this is also called the derating. For component it is derating. Whenever the time is when the time is increased, so the performance it degrades. So, this is also called the derating. So, obviously, you see when t tends to infinity, your R infinity tends to 0. So, which we said, that is the no product can perform for infinite period. So, now you see whatever we said, this gives the probability function for failure. So, probability failure. So, you see at t is equal to 0, at t is equal to 0, f t is equal to 0. So, there is f t 0 means there is no failure. So, the reliability 1. So, you see this is important to see that at any time. So, you consider any time, suppose if I consider a time say maybe a t 0, if I take same time t 0 here, if you add these two, this will give me what I mean to say that if I take f t 0 plus r t 0, this will be equal to 1. Now, the t 0 can be from 0 to infinity. Okay. So, that is why you know this f t and r t, that is the probability, that is the reliability and the reliability and the failure function, the failure probability, the failure functions are complementary. What does it mean? That is, I can write f t plus r t is equal to 1. Okay. So, now so this is a probability density function. So, it is we will see that, or you know this is which curve. So, this is a bell shaped curve, means it is a Gaussian function here. So, we will use those thing in subsequent whenever we will go through this topic, but it shows you know this is. So, this is the mean value, but what is important from here, you see that if something is failing from 0 to t, so you can find by integrating this function. So, suppose you want to find, so at any time t, that is it is not functioning, or the failure at any time t. So, you can find this f t by integrating it. So, you have to integrate from 0 to, suppose you are taking t is equal to capital T here. So, you have to take 0 to capital T and then integrate it f t dt. Okay. So, if you integrate this and you plot it this function, so you will get like this. So, first at t is equal to 0 it will be 0 and then it will accumulate like this, and when it goes to infinity it will reach to 1. So, now suppose this probability failure function is there. So, what you need to do, so you can calculate this by integrating this f t, and then from there you will be able to find the r t. So, r t, how can you find it? So, you can do you know either 1 minus this, you can do is 1 minus this. So, 0 to t f t dt will get. So, what does it means? Now, this t is greater than this t. So, this way you can do the calculations. Generally, for this Gaussian or the normal distribution, there is a tables are given. So, in order to use those tables, you should know you know this complementary function. How I can use the from the probability of the failure, how I can find the you know the probability of success by using this, because you know the total area under this curve is equal to 1. This is given by that because the probability density function, whenever you do 0 to infinity f t dt, that will be equal to 1 always. So, again from here I can write my f t is equal to f t. How can I find it? F t I will find it by d of by dt, that we did it I said in the last class also. So, I can use, since f t plus d t is equal to 1, since f t plus r t is equal to 1. So, I can write this is equal to minus d of r t divided by d t. So, this is a very important you know this expression that also we will be using subsequently. Okay. Now, we will define a very important function that is called the failure rate or hazard rate, and we will see how to derive that. So, let us name is a hazard rate, hazard or failure rate. Okay. So, why what is the reason for the what are the causes for the failure, causes for the failure of a product. Okay. So, the first one is the inherent design weakness. And the second cause is manufacturing or quality control issues. Third can be the because of the environment, there can be variability in the environment which was not envisaged earlier. Then there can be the issues with the maintenance policies, or this the last one, it can be this improper use or abuse of the product. So, suppose you are using a product or something overrated, suppose something is used, there is some specified the operating conditions, when you are going beyond that, also it can fail. So, now that is why it is important mathematically to understand what is the failure or the hazard rate. So, for that what we will do, we will again suppose that n items are put on a test at t is equal to 0, and let n s t the random variable which denoting the number of products which are functioning at time t. So, if you do that, then now you see this is the case we are considering as success and failure. So, we can use either binomial or the Poisson's distribution here. So, this NST which is a random variable here, its probability distribution we can take it here either binomial or Poisson, and as I already said, the expectation, that is the mean of NST is equal to the number of components. So, before that I will use that symbol. So, this represents, this is the mean or the expectation. So, this I can write as n into RT, where n is the number of items and RT is the, or you can say this is the sample size, that is the n is the sample size and RT is the probability, that is n into p, means we are writing that the mean value mu is equal to n p. So, from there I am writing like this. So, I can write my R t is equal to n s t by n. So, I am writing this. So, this is actually n of n s t. So, R t is equal to n s t by n. Now, we will differentiate no, before that I will write f t. So, what is f t? F t is equal to 1 minus R t. So, this will become 1 minus n s t by n. So, which will be equal to n minus n s t divided by n. Okay. So, now if I differentiate this, differentiating f t will give me the probability density function of the failure probability density function. So, differentiating f t, we get f t is equal to minus d of f t by d t. Okay. So, which is equal to if you do this here the differentiation with respect to t. So, what you will get? You will get minus 1 by n. So, this is 1, it is 0. So, it is 1 by n, then it is d of n s t divided by d t. Okay. So, I can write this f t is equal to minus 1 by n, then d of n s t divided by d t. So, this I can write is equal to limit delta t, this is the time step, delta t tends to 0, then this differentiation n s t, or I will put a minus sign here. So, n s t plus delta t minus n s t divided by n delta t. So, this n and this delta t. Okay. So, now what we will do here actually basically this as if you are normalizing this with respect to in terms of the size of the origin. So, this is your original population, okay, and this is the mean at time the t. So, now if we substitute n s for n, then we define the term failure rate or hazard rate, we define the term failure rate or hazard rate So, we will write it using this expression. So, we will write that use some other function. So, we will use h t, the hazard function will use h t is equal to limit delta t tends to 0 n s t minus n of s t plus delta t. So, what we have done So, this minus we have taken inside. So, we are writing it NST minus NS of t plus delta t divided by NST delta t. Okay. Now, our FT, in FT whatever we have derived, this NST was not there. So, I can write now this in terms of FT. So, how I can do that? I will use it limit delta t tends to 0, then I will write NST minus NS of t plus delta t divided by n into delta t. So, this already we have, this is our FT. Now, since I have put n here, so I should get n in the numerator and then divided by this NST. So, now what is this? So, this is actually FT and this is what? This is 1 by RT, because RT is our NST by n. Okay. So, this is an important relation, that is the hazard function H t is equal to F t by R t, which also we will be using in deriving or in subsequently this hazard function. Some books or somewhere this hazard function also used like this. So, we will use either of this either of this expression. So, I will end here, and in the next class I will go from here only, that is the hazard function, and then we will calculate the mean time to failure and go further, but we have started the basics. So, these are the things we will continue. Thank you very much.